Hey, this is an audio reading of chapters 6 through 10 review of atmosphere. I'm going to just read them out loud, and you can follow along with the slides or just listen in. So let's get started. What causes pressure variations and winds? Wind is a horizontal motion of air across Earth's surface. It is measured in speed and direction. Wind is measured with an anemometer, which measures wind speed, and a wind vane, which measures wind direction. High and low pressures. A high pressure, or anticyclone, goes clockwise and outward. It has divergence at the surface and little to no clouds. Think like your hand model. Low pressure, or cyclone, has counterclockwise and inward convergence at the surface. It's cloudy and has stormy weather. High and low pressure at the surface and aloft. This slide is visual, so I suggest you look at it if you don't know about the pressures. But basically, low surface pressure will be high aloft, and high surface pressure will be low aloft. And it goes from high to low. In a sort of circular motion. Let me find my slide back here. All right. Forces affecting wind. This is another visual one, but if you imagine 3 arrows, one is pointing upward, one is pointing downward, they're connected at the middle, and one is pointing to the right. The upward arrow is your pressure gradient force. The downward arrow is your Coriolis force, and the right arrow is your geostrophic wind. Now, that is the air aloft, because there's no friction. If there is friction, then you'll have 4 arrows. You'll have the pressure gradient force going upward. You'll have a southeast arrow with real wind. You'll have a I think I reversed that. So friction and real wind are going to be opposite of each other. Friction is going to be southwest, and the real wind is going to be northeast. That's what I meant to say. So southwest is friction, northeast is wind, and they are opposite of each other. And then you have the Coriolis force, which is pointed at an angle. I suggest you look at the slide. You'll understand. It's pointed more southeast. Let's see. Pressure gradient force. Isobars close together have a steep gradient with high wind speeds. Isobars far apart have a gentle gradient with low wind speeds. think of it when you see all the lines packed together. That's when you'll know it's going to be windy. Coriolis force varies with latitude. So if you remember Coriolis force, that's the force that makes an object turn because of the Earth's rotation. If you take a pen and rotate it and move your finger down it, you will see how that works. The higher latitude has larger Coriolis force. At the equator, there is no Coriolis force. Coriolis increases with latitude. So higher latitude, larger Coriolis force. Lower latitude, smaller Coriolis force. Friction. You probably know friction pretty well. It's when basically something is rough and preventing movement across it, making it a little more difficult. Ice is slippery because it doesn't have friction. Air hockey has a puck that moves across the board because there's no friction, there's less friction. And in the air aloft, there is no friction because there's nothing there to create friction. Where at the surface, we have a lot of textures on the Earth that create friction, and that affects the wind at the surface. Sea and land breeze. So a sea breeze has low pressure on land on the surface, high pressure aloft, low pressure over the sea, and low pressure aloft over the sea, and high pressure at the surface of the sea. And one way you can think about it, one way I think about it is on daytime land has low pressure at the surface. And cold air comes in from the sea in a sea breeze because the water takes longer to heat up. So that land has heated up from the sun much faster than the water has. So cold air is coming from the sea onto land. A land breeze is in reverse. It has high pressure on the surface of land, low pressure aloft, high pressure aloft over the water, and low pressure at the surface of the sea. And because the water holds the heat all day, it absorbed all the heat and it has held on to it, but the land didn't. So the land is now cold. So cold air comes from the land onto the sea. And it has low pressure because it's warmer. That is a land breeze because the cold air is coming from the land to the sea. Mountain and valley breeze. During the day, air above mountain slopes is heated and rises, creating a valley breeze. So the cool air sinks and the valley breezes go up the sides of the valley and warm air rises. At night, that's a valley breeze. That's during the day. At night, air above the mountain slopes cools rapidly and drains into the warm valley below, creating a mountain breeze. So cold air sinks and the warm air rises. That's a mountain breeze. Global wind circulation, 3-cell model. The 3 cells are Hadley, Ferrel, and Polar. Named after Hadley, Ferrel, and the poles. Jet streams. There are some pictures here that you can look at, and one is of the polar jet stream, which in the summer is higher than in the winter. Because of the sun's location heating the land. It's colder in the winter, so the polar jet stream can move downwards because the sun is not. Alright, I don't know if I'm explaining that well, so I'm going to move on. Types of air masses. So, air masses are classified based on 2 variables. The first letter is the nature of the surface in the source region. The first letter is basically where it came from. Did it come from the land or did it come from the water? M is for maritime, that's water, and C is for land, that's continental. The second letter is about temperature. So the ones we are focusing on for the exam is P, T, and A. Polar, tropical, Arctic. We have air mass types. Continental Arctic is very cold and dry. Continental Polar is cold and dry and forms in the winter. Maritime Polar, polar high and subpolar low, is cold and humid. Continental Tropical is hot and dry and forms only in the summer. And Maritime Tropical is warm and humid. Air mass modification. So modification is when one air mass moves over a surface that changes its basically its construction and its origin. So in this example, we have a continental polar, CP, that moves over water. It is modified to an MP, which is maritime polar, because it travels over the water, and when it hits the next point of land, it is an MP instead of a CP. as it was originally. Okay, fronts. A warm front has a red, not sure how to describe it. It has the red line with the bumps on it. A cold front has those blue jagged teeth looking things. A warm front has a shallow slope, cirrus, alto, and stratus clouds, steady rain, snow, or ice. It can rain or precipitate. It has precipitation for a day or more, and it's relatively slow. Where a cold front is steep, it has cirrus and cumulonimbus clouds. It has intense showers and potentially severe weather. The precipitation lasts for a few hours and it's relatively fast. A stationary front has both jagged teeth and the blue jagged teeth and the red bumps. And an occluded front is purple. And it has both of them in purple. Mid-latitude cyclone formation has 4 stages: cyclogenesis, open stage, occluded stage, and dissolving stage. So, when a cold front is approaching, winds turn to northwest, low temp and humidity, cumulus clouds with heavy rains have passed. When a warm front is approaching, winds turn to southeast, temperatures increase, and cloud cover thickens and lowers. Within the warm sector, which is in between, if you think about the jagged teeth are coming in a curve one way and into the cyclone, and the warm front in red joins up with it at the center of the cyclone. Think of it kind of like your hands coming together in a little, almost like a curvy A shape, a triangle. The warm sector is in between the middle of your triangle. Inside the warm sector, winds turn southwest. It has high temperatures and clear sky. Ingredients for thunderstorms. All thunderstorms require 3 ingredients: moisture, instability, and a lifting mechanism. A severe thunderstorm requires 1 additional ingredient: wind shear. Shear is winds that change direction with height. Stages of a thunderstorm. The cumulus stage is dominated by updrafts. The mature stage has updrafts and downdrafts equally with rain. And the dissipating stage has downdrafts, light rain, and updrafts sort of above freezing level. And basically, the mature stage is when the worst part of the storm is happening. And the dissipating stage is when it starts to dissolve and isn't so much of a storm anymore. Formation of a tornado. So the basic requirements are instability at the surface, uplift leads to an updraft, needs warm, moist surface air, vertical wind shear, change of wind direction with height, strong upper winds and weak surface winds, and a mesocyclone, which is a horizontal rotating body of air generated by differences in wind speed. And that looks like it's it for the chapter 6 through 10 review.